Okay, let's continue. All right, so the case of the magic bullet. He was scanning his back catalog of guns and ammo into delicious library when there was a knock at the door and she walked in. A 5'6" blonde with a good laptop bag and cheap shoes. He could tell she was a code jockey. You've got to help me. You got to clear his name. Jimmy was innocent, I tells you. Innocent. He passed her a tissue to wipe the tears from her baby blues and led her to a seat. It was an old story. She'd met a guy who knew a guy. Jimmy Blomstein worked tables at the local Starbuzz and spent his weekends cycling and working on his taxidermy collection. Odd fellow. He hoped one day to save up enough for an elephant. That's really bad. But he'd fallen in with the wrong crowd. The masked raider had met Jimmy in the morning for coffee and they'd both been alive. So I guess, yeah, Jimmy died and they're trying to find out who killed Jimmy or something like that. So anyway, let's look at the code. So we're going to declare a string masked raider alive. Jimmy, in this case, is going to point to the base address where masked raider is. So they're both pointing to the same alive value. Let's kind of bring up our workspace. I had restarted my computer because of an update, so you don't see that icon anymore. Scala-draw. Cool. So, again, our favorite. Ooh, that's odd. Our favorite rectangle. Then we'll have something called live. And then we'll have masked raider pointing to here. And then we'll have something like Jimmy pointing to where masked raider is pointing at. So, oops, Jimmy. Okay. So printf masked raider is alive and Jimmy is alive. Okay, let's move on. Then that afternoon, the masked raider had gone off to pull a heist. Like 100 heists he'd pulled before. But this time, he hadn't reckoned on the crowd of G-men enjoying their weekly 3-card Monte session in the back room of the Head First Lounge. You get the picture. A rattle of gunfire, a scream, and moments later, the villain was lying on the sidewalk, creating a public health hazard. So basically, masked raider is now D-E-A-D! Exclamation point! So, oops, I forgot to also do that. So now we change it to D-E-A-D! Exclamation point. Okay. So the problem is, when Toots here goes to check in with her boyfriend at the coffee shop, she's told he's served his last orange mocha frappuccino. The masked raider is dead, and Jimmy is dead. So what gives? How come a single magic bullet killed Jimmy and the masked raider? What do you think happened? Well, of course, if we drew out this chart here or this diagram here, we knew that masked raider pointed to alive, the string, and then we had Jimmy, right? A Jimmy character pointer here pointing to the same place as masked raider, because when we refer to like any character array as its label here, it just becomes kind of like a character pointer, right? Like the base address to it. So when we did masked raider is assigned to the Jimmy character pointer, we're just basically putting them to point at the same value in memory. So That's why I think. So let's see. How come a single magic bullet killed Jimmy and the masked raider? Well, Jimmy, the mild-mannered barista, was mysteriously gunned down at the same time as the archfiend, the masked raider. So this is the code, but I think it's pretty straightforward. It took the detective a while to get to the bottom of the mystery. While he was waiting, he took a long, refreshing sip from the head-first brain booster fruit beverage. He sat back in his seat and looked across the desk at her blue eyes. She was like a rabbit caught in the headlights of an oncoming truck, and he knew that he was at the wheel. I'm afraid I got some bad news for you. Jimmy and the Masquerader were one and the same man. No! She took a sharp intake of breath and raised her hand to her mouth. Sorry, sister. I have to say it how I see it. Just look at the memory usage. He drew a diagram. Yep, similar to what we have. Jimmy and Masquerader are just aliases for the same memory address. They're pointing to the same place. When the Masquerader stopped the bullet, so did Jimmy. Add to that this invoice from the San Francisco Elephant Sanctuary and this order for 15 tons of packing material, and it's an open and shut case. Yep, that seems pretty obvious. Okay, bullet points. So if you see a star in the variable declaration, it means the variable will be a pointer. String literals are stored in read-only memory. So literals, not the character, right? So we did something like star s. Okay, that would be in global, or not global. Sorry, constants. But we did something like that would be in stack. Yeah, so that's a good review. If you want to modify a string, you need to make a copy in a new array. So that's what we did here. You can declare a character pointer as constchar to prevent the code from using it to modify a string. Okay, so what they're saying is basically when we just do this, we have like a file, right? Or like have a function, we can also like let's do it. We can kind of declare a string to be like this to kind of just tell us that, okay, we attempt to do something like this, where x, maybe x plus 2 is going to be b, for example, right? If we try to compile this, the compiler will give us an error because it's super obvious that it's supposed to be a constant. Versus if we did this, right, we would be able to compile, but this would give us a segmentation fault. We run it. So with the other way of doing it with const character, this would not compile at all, and we would actually know what we're doing is wrong before we even get away with it. So, okay, next one. I don't know, dumb questions. Why didn't the compiler just tell me I couldn't change a string? Because we declared the cards as a simple character pointer. The compiler didn't know that the variable would always be pointing at a string literal. Because we declared cards as a simple character pointer, the compiler didn't know that the variable would always be pointing at a string literal. The compiler didn't know that the variable would always be pointing at a string literal. Okay. Oh, okay, yeah. That makes sense. Hey, why are string literals? That was just what we talked about. Why are string literals stored in read-only memory? Because they are designed to be constant. If you write a function to print "hello world," You don't want some other part of the program modifying the hello world string literal. That's true. Do all operating systems enforce the read-only rule? The vast majority do. Some versions of GCC on Cygwin actually allow you to modify string literal without too much complaining, but it is always wrong to do that. Cygwin, it was like before WSL, Windows Subsystem for Linux on Windows. Um, Cygwin was like the way to run Linux type things on Windows. It was like some layer that contained a lot of the equivalent tools that you would normally run on a Linux computer. So it was like way back in the day. But nowadays we have WSL or Whistle to help solve that problem. What does const actually mean? Does it make the string read only? String literals are read only anyway. The const modifier means that the compiler will complain if you try to modify an array with a particular variable. So it's like a hint for the compiler. It's not really like it's there. It's like a safety mechanism. So, do the different memory segments always appear in the same order in memory? They will always appear in the same order for a given operating system. So I think they're talking about this chart here, this one here, the stack heap global constants code thing. That will usually appear the same way in um, a specific operating system, but not necessary for all operating systems. So but different operating systems can vary the order slightly. For example, Windows doesn't place the code in the lowest memory addresses. I still don't understand why an array variable isn't stored in memory. If it exists, it surely lives somewhere. When the program is compiled, all the references to array variables are replaced with the addresses of the array. So the truth is that the array variable won't exist in the final executable. That's okay because the array variable will never be needed to point anywhere else. So the compiler kind of just substitutes, like it kind of hard codes those array variables to like it'll when your compiler runs through its like I guess parsing or whatever, it'll actually take the address of that array variable and substitute those references to it with that address. Guess that's what it means. If I set a new array to a string literal, will the program really copy the contents each time? If I set a new array to a string literal, will the program really copy the contents each time? Oh, it depends. It's down to the compiler. The final machine code will either copy the bytes of the string literal to the array, or else the program will simply set the values of each character every time it reaches the declaration. You keep saying declaration. What does that mean? A declaration is a piece of code that declares that something, a variable, a function exists. A definition is a piece of code that says what something is. If you declare a variable and set it to a value like int x equals 4, then the code is both a declaration and a definition. So this is a declaration. This is a definition. So we should probably write that. Okay, this one is a definition. And then this one here is both a declaration and a definition. Okay, so int x declaration x equals 4's definition, and x equals 4 is both a declaration and a definition. Okay, I need to start using these words correctly. Okay. Why is scanf called scanf? Scanf means scan formatted because it's used to scan formatted input. Cool. All right, so here is I guess now they're going to actually define or at least go into depth of this memory map here. So let's read that through together. Um, Stack. This is a section of memory used for local variable storage. Every time you call a function, all of the function's local variables get created on the stack. It's called the stack because it's like a stack of plates. Variables get added to the stack when you enter a function and get taken off the stack when you leave. The weird thing is the stack actually works upside down. It starts at the top of memory and grows downwards. So it's kind of like what we've done here all this time. It's like every time we add stuff, it just goes downwards like this. But I think when they say downwards, I believe the memory addresses are subtracted, right? Like that, and so forth. Okay, so now let's go to heap. This is a section of memory we haven't really used yet. The heap is for dynamic memory. Pieces of data that gets created when the program is running and hang around a long time. You'll see later in the book how you'll use a heap. So actually it's interesting because I think for some systems, maybe even like this one too, like you have a stack that grows downward, but you also have a heap, I think, that grows upwards. And then eventually they will kind of meet and you get bad errors if the stack tries to go beyond what's allocated or like its maximum capacity. And I think that's where you get like stack overflows and things like that. Um, Globals. A global oh, by the way, and this here is way bigger than stack. Okay. Okay, globals. A global variable is a variable that lives outside all of the functions and is visible to all of them. Globals get created when the program first runs, and you can update them freely, but that's unlike constants. Constants are also created when the program first runs, but they are stored in read-only memory. Constants are things like string literals, but you will need them when the program is running. Will you are literals that you will need when the program is running. But you'll never want them to change. So you can never change constants because they're constants. Finally, the code segment. A lot of operating systems place code right down in the lowest memory addresses. See, lowest. So that is proof that these memory addresses actually go lower, even though we've been making them look like they grow bigger. So if you go 1,000 here, you'll have 500 here, you'll have 0 here. So I believe everything else just grows upwards, right? Except for the stack where it actually goes downwards. And that's why you have something called a stack pointer that actually tells you like the current memory address of where the stack is. But I think that's like details to learn later. Anyway, we'll skip that. Okay, so on to the next chapter, string theory. Okay, so before I want to go on to that, I kind of want to clarify more pointer stuff in that it's time to start thinking about them a little bit differently than what we've kind of visually drawn because I've been trying to keep consistent with the diagrams found in the book. But real quick, let's say I have like an int uh, pointer, right? Yeah, answer. Okay. So let's say I have an int pointer, let's say x, that points to some address k. So let's say I have k is 99. And if I draw the memory here, right, I have 99 here, which is going to be k. Okay? Now let's say this is memory address, I don't know, 55. Oops. Okay. That's memory address 55. When I say int x is going to be a variable, a pointer variable that stores the address of k, what is really going on is that somewhere in memory, really, maybe memory address, I guess if this is now growing upwards, this is going to be 52. That doesn't even make sense, but okay. um, let's just say, yeah, just give arbitrary addresses. What it's saying is that now, if K is at address 55, it's an alias for 55. X is an alias for 52. What's saying is that now in here, we just store the address, right, of K. Right here, get the address of K, which is 55, and store it as the location at pointer X. So really, it looks like this. And then that's the reason why we kind of draw it this way, right? So that's how it really looks like in memory. I know we've been doing like the other way around where we have like these two things and we kind of just like, this way I just pointed to this and so on. But really, a pointer variable is also like any other variable in memory. It takes up its own spot too, and it stores the value. The value would be the memory address of whatever it is pointing to. Okay. So, yeah, just wanted to clarify that that's how we should actually be thinking about it going forward. Um, okay, so string theory. So we're gonna work with strings now. Yay! We're gonna start to be able to maybe create more useful things. Um, cool. So let's try to understand this joke. Stircomp says we're identical. I thought it called you short and said your butt was bigger. Okay. I still don't get it, but okay. I think stir comp is supposed to be like a string comparison thing, but I'm not sure why, you know, calling someone short and their butt being bigger would be funny. But okay. So there's more to strings than reading them. You've seen how strings in C are actually character arrays, but what does C allow you to do with them? That's where string.h comes in. So string.h is a new library that we're going to be using, a new header. So you know how we were like including stdio.h, and then sometimes we were including stdlib.h. This is going to be new header.h that we're going to be including. Um, so that's where string.h comes in. String.h is a part of the C standard library that's dedicated to string manipulation. If you want to concentrate, or if you want to concatenate, meaning taking two strings and putting them together, combining them, copy one string to another. So taking one string and copying it to another place in memory, or compare two strings, seeing if the strings are equal. The functions in string H are there to help. In this chapter, you'll see how to create an array of strings. So a list of strings, and then take a close look at how to search within strings using the str function. So str, I believe, is just to find, given some large string and some other string, find to see if if that other string occurs into that large string. So I think we took a look here and look at for str. We'll see. Yeah. So finds the first occurrence, and it'll give us back the memory address. It looks like, yeah, pointer to the first character of the found substring in stir. So stir. Null. We had to remember this. Yeah. Cool. Um, Desperately seeking Frank. There are so many tracks on the retro jukebox that people can't find the music they are looking for. To help the customers, the guys in the Head First Lounge want you to write another program. This is the track list. Okay, so this is a list of songs. I left my heart in Harvard Med School. Newark, Newark, a wonderful town. Dancing with a dork. From here to maternity. The girl from Iwo Jima. So this is going to be a list of strings. Okay. The list is likely to get longer, so there's just the first few tracks for now. You'll need to write a C program that will ask the user which track she is looking for, and then get it to search through all of the tracks and display that match. Okay. So now we know we'll have so like our requirements already is that we'll have an array. So let's start a new project. And let's digest the requirements. So let's do this. Tracks, music tracks. All right. Then we'll create a new file. We'll call it main.c again. And then we'll write our standard template. cio.h. And then let's do int main, int argc, character, argv. And then I wonder if we should just like make it like this instead. Let's be consistent with our notation. Return 0. And then we'll have a tracks list. So we'll have given a tracks list. Write a C program that will ask the user which track she is looking for. Get that input and use it to search through all tracks. Display any matches. So what is a match? A match is basically when input exists within the track string. So like an occurrence. When input occurs. So we're going to have to use stir. That's the hint, right? Didn't hint. Stir, maybe. Okay. And we're gonna use loops, right? So here's loops. Okay. So here they're giving us code. So create an array of arrays. That's the first step. There are several track names that you need to record. You can record several things at once in an array, but remember, each string itself is an array. So it's an array of arrays. So an array of character arrays. Okay. That means you need to create an array of arrays like this. So in each element in this array, this tracks array, you're going to have an array that is a maximum of 80 characters. So that's what it means here. Okay. So right now, since we have 5 strings, it's like kind of obvious, right? Similar to, when we define any other array, whenever you're explicit about all the elements in it, you don't need to define how many there are. The compiler can figure it out by counting it. But this one is like you need to give like inside each element in this array, right? You have another array inside. Well, what is the maximum length of this array inside that array? So that'll be 80 characters. So the array ends up looking something like this. So this is the first element in that array. This is going to be the second element. So let's say, if I'm looking at the third element in an array at index 2, which is going to be this string, this dancing with a dork. If I say I want the, fourth element, so 0, 1, 2, 3, this is the fourth element, right? Since it's 0 index, it'll be C, right? So that notation is going to be go to index 2, then index 3 in there. And notice how, like, we said 80 characters maximum. well, any character after the last character of that string is just gonna be filled with zeros, which is gonna be a null character. So as long as we don't go over 80 characters. So yeah. So why don't we do this? Why don't we just copy and paste this code into here to define the tracks list? So we can just paste here. And then now we have our tracks. Cool. I wonder if I can condense this in Visual Studio to make a tab instead of 4 spaces. Let's try to make it 2 spaces so we're a little bit more compact. So tab space, yeah, tab size. Let's make it 2. And so now going forward, we won't waste so much space in tabs. So let's format our document. I wonder if we can just do prettier here and it'll help us. Tab prettier RC. Prettier RC will actually help us with our auto formatter. Is it tab size? What is it? I need a prettier extension. So I have prettier RC. I need the prettier extension maybe. Yeah, I do need a prettier extension. So let's do that. Let's go back to our prettier RC. Tab space. What's it called? What's it called? Let's see. Let's reload our extensions. Okay. This should work. Unless I don't have a default formatter. Let's see. Let's look for settings again. Default formatter is going to be prettier. Maybe that's the reason why. So prettier. And then let's do a format on save. Right there. So then when we save, we'll automatically format. So now, do we have anything? Or is it like a JSON? Oh, there it is JSON. Okay. So space tab width is going to be 2. Okay. So we did this. Will we get an adjustment? How about if I just did this? Then, but my tab width is 2. I gotta. Okay, whatever. Maybe I need to restart. Let's see. Whatever. We'll just leave it be for now. We gotta figure that out soon. Maybe prettier is only for like the web or something. Okay. Okay. So we have our array. Now, let's see if we can code this ourselves. Let's see if we don't need the book, right? So let's see. Ask the user which track she is looking for. And I remember when it comes to that, we weren't supposed to use scanf to receive user input. We were supposed to use, I think, getS or fgetS. I think it was fgetS. So if we look back at our reference, we see that we have an example here, fgetS. So reads at most count -1 characters from the given file stream and stores them in a character array pointed by stir. Okay, so this will be stdin maybe? Or is it sgetS? Or is it sgetS? Or get it is fgetS, yeah. So that'll be stdin maybe, and then this will be the string pointer. So the character pointer we want to store as a string, and this is like the maximum amount we want to read. So I think example here is this all files. Or is it fscanf? I think it's fscanf. No, that's files. I totally forgot what we just did. That's the reason why we do a lot of examples, right? Scanf demo. This one was not the good one. This one, fgetS. Yes, it's fgetS. So cool. Cool that we have at least references here for ourselves because we've done it a while. So yeah, we'll just ask, we'll prompt for a song, and then we'll have this fgetS to store into a character array, maximum 80 characters, and then a cdn. So remember, we don't need to do one less character because fgetS will automatically give us a null character at the end because it will only read at most, like the doc said, at most count minus one characters, right? So going back to here, fgetS reads at most count minus one characters. Okay, so we'll ask printf, what is your song? And then we'll say fgetS, so we'll have a pointer char input, and then we'll say input at most 80 characters to scdn, something like this, I guess. Okay, and oh, we can't do that, we have to do an array, something like this. Yeah, input with 80 blanks, 80 blank characters. We ask for some input, 80 characters at most, into from keyboard input, store that into this buffer here that we've created. Okay, so that's so far okay. And then now after this, we at least have input, so we can test it out. We can print f %s input, and let's see if we get back the same thing we inputted. So let's test first. So we go to our code, cd, I think it was music tracks, gcc main.c, as a song, hello, hello, world, world, hello. Okay, so we got that echoed back. But notice here again, fgetS probably takes in the new line because we hit return. So that's new line, and it's out. It actually has a new line, and we get an extra line here because we're actually right here. We're printing out that new line here, right? So we get rid of that and do the same thing again. We only get one new line now, right? So gotta remember that. So given that input, can we use stir to search for anything in here? So we have input now, and we should probably check if input is null because chances are we could have a null pointer, right? So it's like here, return value, null pointer on failure. So we always have to account for these types of cases. So we'll say printf, something bad happened. Then we'll print a new line, and then we'll return 1. We can't proceed anymore because something bad happened. So at this point, or it's not input, it's result. So what is it? How does this return? Oh, return the string. So input itself. Okay. So yeah, I think that's okay, right? Or we can actually do it this way. We could do it this way because the data will be an input anyway. So maybe that's the way to do it. Yeah. So we'll we'll call fgetS to read keyboard input to put into this input buffer here, And then whatever this returns, we can check for null pointer. And if it's a null pointer, we can output something bad happened, and then we could just return 1 to get out of the program. Otherwise, we can, what did we say? Get that input and use it to search through all the tracks. And we can use this new thing called stir, which I had hinted already. So use a loop. So how many tracks do we have? 1, 2, 3, 4, 5. 5 tracks. So we can do a for loop for int I 0. I is less than 5. I plus plus. And we could say character per track is going to be tracks at I. So taking a 0, 1, 2, 3, 4, less than 5, right? At 0, we get this string. At 1, we get this string. At 2, we get this string. At 3, we get this string. At 4, we get this string. Okay. Now, display any matches. So we use stir. Or let's see if we can actually print out the tracks first. Sorry, go back to code, printf. So we'll print the current track. Let's just iterate slowly. And then we compile and run again. We'll say hello, hello. That doesn't matter. But here, we're able to print out all our songs. So that's good. Now we want to figure out like whether or not our input, we want to take our input and check against the current track and see if there's an occurrence of input inside that track. And if there is, then we can print it out. So I think we can use str, str. So let's read this. Finds the first occurrence of the null terminated byte string pointed to by substr here in the null terminated byte string pointed by stir. The terminating null characters are not compared. So null characters aren't counted in this comparison. That's what they're saying. So you gave like, I don't know. You have to have a null character though to tell it to stop. But yeah, just I guess we should know that. So given this bigger string here, given this smaller string here, find that the smaller string occurs inside the bigger string. So pointer to the null terminated byte string to examine. Pointer to the null terminated byte string to search for. So search for, this substring. Okay. So return value. Pointer to the first character of the found substring. So it'll point us against just like strchr if we had a string world, and then we had world as our string, and then we have maybe orl as our substring, then stir will actually point us to here as a result. So our result. So then if result is null, then ORL does not occur. So looking at the documentation, it says you'll get the pointer to the first character of the found substring, or null pointer if no substring is found. Okay? So if substr points to an empty string, then the entire string is returned. So if we gave an empty string to stir, then we just return back the entire string here. Okay? So knowing that information, we'll need to use stir. So we use stir to check if input occurs in cur track. So we need to include the string library here in order to use stir. There we go. And we can call stir with what? The haystack. So that's like the bigger string. So that's cur track. And then the smaller one, the substring, will be input. And it returns something, right? So we can say it returns a pointer. So basically the pointer to the first character of the string that occurs inside cur track. So result, or just say occurrence. Okay. And I should probably do this because it is technically a pointer to a character, not pointer to cur track or whatever. So now we need to check if occurrence is not equal to null, meaning that we have some match. We should, last requirement, display the matches. So when occurrence is not null, it means that input occurs inside the current track. So we can just printf the string, new line, not the occurrence, but the current track. That means current track matches the intended search. So let's try this out. The GCC. Let's do med. That didn't work. Is it case sensitive? That didn't work. So I wanted med school. Why is that? How about we print it out occurrence? Maybe we're using something wrong. Let's do occurrence. No. Oh no. That's interesting. So cur track, find whether or not input contains is contained in cur track. That should be okay, right? Let's see. So the behavior is undefined if stir or substir is not a pointer to a null terminated by string. How is this even used? Stir, character pause. That's right. That looks right. Character 2 is in here. Huh. I wonder if, again, there's something wrong with because if we're using fgetS, that means our input has a new line character, right? I'm wondering if it is because our new line character is throwing off the substring matching. Like, for example, I wanted for example, let's just do this. Let's say I wanted to get the result. I left my heart. Ugh. I left my, what is it? My heart in Harvard Med School, right? And then I think I inputted, I wanted med. But what I really got with fgetS is med new line, right? Because of that enter key. Now I wonder if it's because now it's trying to match for this inside here, which does contain nothing because technically med/n is not this one anymore. That's why I wanted a match against actually. So I wonder if we should just assume that input should have new lines removed. And remember our trick was to use stir chr on input new line. Ugh. Let's see. Erase. Okay, on input, new line, and then get that occurrence of new and set that to null terminating character. So that's like, remember that trick we did yesterday, I believe, where we took in, I think it was this one. Yeah, we took in input, but then we also removed the new line character because it was making our formatting really ugly. Well, now we have a problem with this new line character here. It's throwing off our substring matching, I believe. And then, yeah, we're not getting results because of that. So we should probably try the same trick here, right? Stir char takes in the string and the character you want to find the first occurrence for. So stir is a string version. Stir char is the character version, right? And if we get something back, it means that that's the location of where the new line character is, and we can just set it to a null character, and that removes the new line character. So what we can do is when we get input here, let's do this. Yeah, this is a good spot. As soon as we know we have input, let's check. So we can say character new line occurrence is going to be stir char. It's going to be input. And we want to check for the new line character. Now, if there is something, that means it's not equals to null, then we kind of just want to set that location. So update that location, which means star new line occur equals null terminating character. So we have that. So in memory, right? In memory, if we think about it, and I'm going to go back to that simplified diagram. If we had something like this, med/n/0, we'll have input here. Okay. And then if we were to find the new line character, we'll have new line occurrence here. And if we set that to 0, then input is going to be this string there. It modifies a string in place. So that's the way I see it. And I think that should solve our problem. We get rid of the new line. We should be able to match. So let's compile again. And then let's type med. And there we go. We have one match here. And I had still continued to print out the occurrence, which makes sense because we don't have meds in here. That's cool. All right. So let's clean this up a little bit. Let's get rid of this one. Let's get rid of this. Actually, let's keep that there. It's good for us to understand the problem. Okay, so let's try another test. Let's try A is a bad one. Let's try girl. Yeah, let's try girl. Let's run it with girl. And we get the girl from Iwo Jima. Okay, let's try here, from here to maternity. Let's try dancing with the, and dancing with the dork. Let's try A, which we get pretty much everything, because everything has an A. And then let's try one more. In. Okay, so dancing with a, CININ here occurs. This occurs. So I think we've hit the requirements. So let's go back here. And this tells us how to actually reference the array, which I think we already know. So just do that reading. Anyway, find strings containing the search text. the guys have helpfully given you a spec. Ask the user for the text she's looking for. Loop through all of the track names. If a track name contains the search text, display the track name, which we had right here too. So this is how we were able to. I mean, it's fun to do it without the answer, right? So, well, you know how to record the tracks. You know how to read the value of an individual track name. So it shouldn't be too difficult to loop through each of them. You even know how to ask the user for a piece of text to search for. So we knew how to do all this, right? It was just very dependent on us being able to put all this together, and which we did. Um, but how do you look to see if the track name contains a given piece of text? So that's the part, right? That's why we needed something new, and that was the stir. So using string.h. The C standard library is a bunch of useful code that you get for free when you install a C compiler. The library code does useful stuff like opening files or doing math or managing memory. Now, chances are you won't want to use the whole of the standard library at once, so the library is broken up into smaller sections. Each one has a header file. The header file lists all of the functions that live in a particular section of the library. So far, you have only really used the stdio.h header file. stdio.h lets you use the standard input-output functions like printf and scanf. And we also use a little bit of an stdlib too. So, but the standard library also contains code to process strings, string.h. String processing is required by a lot of the programs, and the string code in the standard library is tested, stable, and fast. Cool. So we can do things like compare two strings to each other, search for strings, even slice the string into little pieces. So stuff that you would normally use if you were coming in from like a Python or a JavaScript background. It's also possible in C too. Cool. Ooh, let's play a game. I wonder. I think I tried this before. I think Excalidraw doesn't let us. Oh, it does let us insert an image. That is so cool. Let's do that. So let's take a screenshot. This is a cool game. Let's play a game. Ah. Here, let's move the mouse. Okay. Can we resize? Yes, we can. Cool. Let's play a game together. Okay. And let's see how much time I have left. Okay. That's cool. All right. Okay, let's get this out of our way. Let's make this bigger. Actually, let's do it like this. Okay. Okay. See if you can match up each string h function with description of what it does. So this is like, see if you can kind of infer, right, what these actually mean, and then see like the purpose. So we know stir is going to find a location of a string inside another string. So we can match that up here. And then char, we know that one is find the location of a character inside a string. So right there. And then I know strlen. Strlen is probably the length of a string because it reminds me of the Python len file or function. Let's see. This is getting better because we now have concatenate, we have compare, and copy. So I say strcat is concatenate, and stir copy right here will be copy one string, and then stir comp will finally be compare two strings. I think it's this. Let's see what we got. Wow, that does not help. Well, let's see. Can we chuck this here. Yes. Let's see. All good. Okay, great. So, it's just my wife. She's keeps me up to date on the kid. She's on parent duty. Kid duty. Okay. Let's see how we did. Okay, so stir char. Okay, so find a location inside a string. Stir comp compares two strings. Yep. Stir find the location of a string inside another string. Okay. Stir copy one string to another. Stir length find the length of a string. Stir cat concatenates two strings. Nice. So yeah, using the stir function. So how exactly does the stir function work? Let's look at an example. So let's say you're looking for a string fun inside a larger string dysfunctional. You'll call it like this. So stir, find fun inside dysfunctional. The stir function, so notice these memory addresses. Alright, so the stir function will search for the second string in the first string. So second string in the first string. If it finds the string, it will return the address of the located string in memory. In the example here, the function would find that the fun substring begins at memory location 4,000,003. But what if stir can't find the substring? What then? In that case, stir returns the value 0, which is null, right? That's what the capital N, capital U, capital LL. So, I think this here is pretty much equal to 0. Can you think why that is? Well, you remember C treats 0 as false. That means you can use stir to check for the existence of one string inside another, like this. So given this string, check. And then, so if stir returns a 0, which is a falsy value, then don't execute this code. But since it does return something, go into this. I found the fun in dysfunctional. Okay. So yeah, here's basically how they wrote the loop. Let's just jump to the answer. So I think this one is basically the input 80 search for fgetS, which was what we did too. We find track. I think they wrote it in a different function. So find track right here. Okay. So it just basically loops 5 elements, uses stir, and then finds it. How come they didn't search for? How come they didn't run into the new line issue? That's interesting. How come they didn't run into the new line issue? Is it because they're testing it in not the same way we're testing it? They're probably passing it through stdin for real, like redirecting. Interesting. Let's see this. Nah, let's just move on. It's important that you assemble the code in this order. The headers are included at the top so that the compiler will have all the correct functions before it compiles your code. Then you define the tracks before you write the functions. This is called putting the tracks array in global scope. So this is in global memory. We didn't do that actually. We put it all in local memory. So basically inside the main stack, the main function stack. Yeah. Stack frame, whatever you call it. So like, I think how memory is actually really done in stack is like, okay, again, our friend, you have like the stack here, right? I think it's like whenever you call a function, for example, main here, there's like this region called main, and then you have all your memory in here, right? It's these sub regions, right? If you call another one, like let's say find tracks, you'll have uh memory in here too. So yeah. So basically when they put the tracks in global scope, it's gonna be in here. Tracks. Ugh. All right. This doesn't even look like tracks. Let me just ah yeah. Tracks. Put some effort into writing. Okay. So yeah, this is straightforward. I think it's because we've done it already. And yeah, the program works. Even though this program is a little longer than any code you've written so far, it's actually doing a lot more. It creates an array of strings and uses a string library to search through all of them to find music tracks that the user is looking for. It's pretty cool. Oh wow, we could actually use... Oh, this is interesting. For more information about the functions available in string.h, see this. If you are using a Mac or a Linux machine, let's just see where that goes. Okay, that's just GNU manual. So they're hinting at something. They're hinting that we can actually use man pages to look at C documentation. That's so cool. So let's do that. Man stir. And we actually get documentation. That's so cool. Wow. It's it's probably exactly the same thing that we were looking at. Let's see. Yeah, it has like everything. The return value. The expression return a pointer to the beginning of the location of a string or null if not found. And then look, if needle, basically the substring is an empty string, the return value is always the haystack, which is the bigger string itself. That's exactly what we read, right? That's so cool. Yeah. And what is this one? Stir case stir. Stir case stir is like, but ignores the case. Oh wow, this is even better. Stir case stir. That's so cool. So I want to do something. I want to use stir case stir because with our program right now, we did med, we would get nothing, right? I want it to be case insensitive because what if I don't know that it's part of like what if I don't know that the song has like a capitalized letter or not? So let's change it. Let's just see what happens. So instead of stir, let's use stir case stir. And I think it's the same signature too. It's again man stir. Stir case stir. Yeah, it's the same signature. It takes a haystack and a needle. This is so cool. Med. I left my heart in Harvard Medical School. That's cool. Nice. Case insensitive substring. So our program is even better than this book's program. There are no dumb questions. So why is the list of tracks defined as tracks 80 and not tracks 580? You could have defined it that way, but the compiler can tell there are 5 items in the list, so you can just skip the 5 and just put empty brackets. But in that case, why couldn't we have just said tracks, empty brackets, empty brackets? Well, it's because the track names are all different lengths. So you need to tell the compiler to allocate enough space for even the largest. So you have to tell them the maximum characters, which is going to be 80 for our program, right? But not every track is going to be 80 characters. So does that mean each string in the track array is 80 characters then? The program will allocate 80 characters for each string, even though each of them is much smaller. All that is that basically if your string is less than 80 characters, the rest of the elements are just going to be null terminating characters. Okay? So the tracks array takes 80 characters, and we have 5 strings, so it's 80 by 5, 400 characters worth of space in memory. Yes. And so what happens if I forget to include a header file like string.h? For some header files, the compiler will give you a warning and then include them anyway. For other header files, the compiler will simply give a compiler error. So why did we put the tracks array definition outside of the function? We put it into global scope. Global variables can be used by all functions in the memory. So I guess in a sense, it's more memory efficient because if we put it inside a function, every time we call that function, we have to recreate that array in the stack, I guess. So I think that is probably a good thing to do because this is never going to change. So we can just take this and put it out here, and I think that is probably the better way to do it. Okay. Now that we've created two functions, how does the computer know which one to run first? The program will always run the main function first, so we gotta remember that. Why do I have to put the find track function before main? Oh, we didn't do that. We just put everything in here, but that's okay. Um, C needs to know what parameters a function takes and what its return type is before it can be called. So basically it's saying that it's like whenever you have a function, like you call a function inside main or whatever, just make sure it's already defined before main, right? It has to be like it's top down scanning, right? So if you've never defined, or no, let's go back to our words. Let's go back to our words. If you've never declared, okay, a function, then you can't use it before it's declared. So it has to be known first. So what happens if I put functions in a different order? In that case, you get a few warnings. Yeah. You can create an array of arrays with this syntax: character strings, square brackets, square brackets. The first set of brackets is used to access the outer array, so the rows, right? And then this will be the columns, the second one. The second set of brackets is used to access the details of each of the inner arrays. The string.h header file gives you access to a set of string manipulation functions in the C standard library. You can create several functions in a C program, but the computer will always run main first. Yeah. Oh, reverse characters. This is fun. Oh, I want to do this one. Yeah, let's do it. Let's write our own reverse characters. Say print reverse. The guys are working on a new piece of code for a game. They've created a function that will display a string backwards on the screen. Unfortunately, some of the fridge magnets have moved out of place. Do you think you can help them reassemble the code? So let's actually do it on drawing first. So, oh, that's ugly. I'm glad I'm doing this digitally because I think I would have wasted a lot of paper right now, or used a lot of paper. So we'll have, like, let's say a string s. So let's just start any string here. Let's just make it simple. Let's make it cat, right? And then, technically it's not really like this. It's more like someplace in memory, like, s is defined here, and it'll be like, this will be like maybe 1,000, right? So it'll be like 1,000, and this will probably be like, it grows downward, so this will be like 1,003 or something like that, and then it will actually point. So it's more tedious to do it this way, but yeah. Anyway, I'm not gonna even do that. I'm just I said that I would start doing that, but just, as long as we know that's how we should think about it. Um, so we'll have s step points here, and then we'll have size t is just an integer used for the storing the sizes of things. So it's just the size of this string. So let's just say len is going to be So it uses strlen to get the size of this S string, and that's going to be what? 1, 2, 3, 4. Okay. And then we're going to say, well, character T is going to be at something something minus 1. So I have a feeling that we're going to start T. I think I know what it's trying to do. So notice how it's like printing a character is dereferencing whatever T is currently pointing to, right? So I have a feeling that they want to start T here. And then I'm guessing that we want to start T and keep going down until, you see this while loop here? Until T, the address at T is the same as the address at S. So what it's saying is that, if they're numbers, it's just a simple while T is greater than equal to S, right? So remember, they're just numbers. These addresses are just numbers. So we basically want to do some pointer math here by subtracting a character or an address each time. So, T minus 1, T minus 2, and so on, up until we hit this. But what do we start T at, right? So, if S is going to be, let's say, at 1,000, memory address 1,000, this will be 1,001, this will be 1,002, and this will be 1,003. So the math is that we want to start T at what? It'll be S plus len minus 1? Is that true? So 1,004 minus 1 will be 1,003. So we start there. I guess we have to take into consideration the null terminating character. I guess that's fine because it's just empty anyway. It'll print out as empty. So we'll start at that. So it's basically going to be the math here, this part, right, is going to be something like T is equal to S, the address of S, right? So that's already a pointer, so we don't need ampersands or anything like that. Plus our length, because we already defined our length right here, minus 1. So in this case, if it was S was 1,000, we have 4 as our length, minus 1. That evaluates to 1,003, which gets us to here. And then we just move downwards, printing the reverse string. So we can just do that real quick in code. So print reverse string main.c. So again, let's do this. We know we need string.h because we're using strlen, right? So we'll just first include stdio.h, and then we'll include string.h, and then we'll create our main function, and then we'll fill out the blanks. Oops, turn 0. Okay. So we'll have size t, which they told us to never mind about that for now. We need a function. We need to declare the function. Void print reverse character s, and then we'll say size t len strlen s, and then what is this? We said this would be the address at s plus len minus 1, right? And then we'll have a while loop. And we said this, while the address of t is greater than equal to the address at s, we want to print the character dereference the current location. That's where t is pointed by, right? So going back here, we want to dereference, right, with a star. So get the value at this address. Then when we're here, we want to get the value at this address, get the value here, get the value here. So then we'll end up with T, A, C. I didn't have my pen, but okay. So after each iteration, it's simple. It's just t equals t minus 1, I believe. It's a character, 1 byte. Just subtract 1 from the address, and then we'll put an empty string. So let's test that. Let's do print reverse, and then let's give it cat, and let's just see what happens. So print reverse is a function that takes in a string s. We'll get the length using strlen from this library here, right? So if we were to go man strlen, our new trick, the strlen function calculates the length of the string pointed to by s, excluding the terminating null value. Whoa, it's a good thing that we read this. Whoa. Excluding calculates the length of the string. Huh. In cases where input buffer may not contain a null terminating null byte, strlen length should be used instead. Interesting. So we have some assumptions. The strlen function calculates the length of string pointed to by s, excluding the terminating byte. So this should actually give us 3 then. Interesting. And I guess that does check out to our initial assumptions. So let's do it. I'm glad I checked. So if I had this, and I had s, and I said strlen is going to be returning us 3. So this is 1,000, 1,001, 1,002, 1,003. I said t will be, I guess, 1,000 and plus len, which is 3, minus 1. That's 1,003 minus 1, which is 1,002. Oh, we do start out here. That's even better. So that assumption about, oh yeah, it's, no terminating character is blank anyway, we can print it, that probably isn't the case. That we're probably really starting at the character before a null terminating character, because documentation says strlen doesn't consider the null terminating byte to be part of the length. So I'm glad we really checked that, because we can fix ourselves before we run. So, well, nothing changes. We just changed our assumptions, basically. So nothing changes, right? Because if this is 3, then 1,000 plus 3, just 1,000 example for s, minus 1 is 1,002, which is going to be the last character. So actually our code works, it's just that our assumptions were wrong. Okay, so I'm glad we checked. So let's just test it. What is it? Reverse, print reverse string, gcc main.c, a.out, tac. Okay, so what happens if I just do this? argv1, user input, right? Because the 0th element for this argv is our program name, so the first one should just be our user input. So we can generically just do this. Oops. a.out hello, which is ole, and then hello world, which is whatever this is. That's cool. Look, we can reverse a string with a command line argument. We just need to make it better. Like, for example, if argc is less than or equal to 1, then we could say, please provide a second parameter or second argument to reverse. So then let's say if we compiled again and we just ran a.out, we would get this message. Oh, we should probably return. Return 1. Non-zero return code. And then we could do it again. Okay. Hello. Nice. So if we didn't provide anything, please provide a second argument in reverse. Otherwise, we provide something, we reverse. Cool. Let's see. So the answer was this. So let's see how it compares. Yeah, puts, subtract, make sure t is greater than or equal to s, which is basically memory location of t is always greater than or equal to the memory location of s, and we're just decrementing the memory location each time. Yeah. So you've seen how to use an array of arrays to store a sequence of strings, but another option is to use an array of pointers. An array of pointers is actually what it sounds like, a list of memory addresses stored in an array. It's very useful if you want to quickly create a list of string literals. Yeah, we know how to do that. So instead of like an array and arrays, we can just say, well, let's make a character pointer of arrays. So point to the first element of the list of strings. Okay? C cross. I'm kind of tempted to work on this together. Let's do it. Let's do it. Let's do a crossword puzzle, and then I think that'll be it. We'll call it a day. Yeah, let's do that. Okay, how do I get the screenshot with everything? Let's just C cross cross down. Okay, so let's just make it like we don't have information here. Okay, let's just take a screenshot. I wonder what we were supposed to do here. Oops. Move this. Make it real big. Okay. So we have code here. Okay. So I guess we have to print out the output. And I'm going to make ours blue. Okay. So character array that contains, I guess, strings. So pointer to an array of strings. Okay. And then we have just one string, it looks like. Then we'll put s juices 6. So take this array and find the sixth element. So there's 6 elements, 0 index. 0, 1, 2, 3, 4, 5, 6. That's mulberry across. So 1 across will be mulberry. Mulberry. Okay. And then number 2 is print reverse juices 7. So assuming our reverse code works, so 0, 1, 2, 3, 4, 5, 6, 7 strawberries. So let's reverse that. And that is across. What? Oh no, that's 2 across. So Y R R E B W A R T S. Okay. And then A is now going to be, A is going to be what? Y R R E B W A R T S. Okay. Just so that we can, wait, juices 2. Juices 2. Sorry. I was reading still the answer. Juices 2 is 0, 1, 2, Sharon fruit. Okay. So now juices 2, so juices 8 is going to be assigned to juices 2, 0, 1, 2, 3, 4, 5, 6, 7, 8. So juices 2 is going to be what? I already did. 0, 1, 2, 3, 4, 5, 6, 7, 8. Blueberry. So we change that to blueberry. Okay. Juices 8 is now A. So juices 8 is now Sharon fruit. And then we'll put S juices 8. So 3 across is going to be Sharon fruit. Okay. Then we'll print reverse. Holy crap. Juices 18 plus 7, 25 divided by 5. So juices 5 is going to be 0, 1, 2, 3, 4, 5 kiwi fruit. So 4 across is kiwi fruit. Okay. And then down, put S, puts juices 2. We said juices 2 was blueberry. So 5 down should be blueberry. Blueberry. And print reverse juices 9. Juices 9 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Reverse of juices 9 blackberry here is going to be, oh geez, 9 down? Where's 9? Wait, sorry. 6 down. 6 down. Okay. Jeez. Okay. Y R B K C L B. Okay, now 7. Oh, so juices 1 is now juices 3. So 0, 1, 2, 3. So ugly fruit is going to be juices 1. Okay, now print juices 10. Juices 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Star fruit, which is going to be 7 down. Star fruit. Cool. And then now, last one is going to be reverse juices 1. So that is ugly fruit in reverse. So T U I T. What? Did I mess up? Oh no. Is it really ugly fruit? Hold on. Juices 1 is juices 3. 0, 1, 2, 3. Ugly fruit. Huh. Everything worked out except for this one. Did I? T I U? Is that just the R? Oh man, I'm tripping. 0, 1. Oh, wait. This one is, let's debug. Where did we go wrong? Waterberry. It cannot be waterberry. So juices 1 is juices 3. 0, 1, 2, 3. Did we ever modify 3 here? No. Oops. No, whatever. This is for fun. I'm just gonna do it this way. U G L I F. Pretend that's an R. Let's see. All right, let's just see the answers. That's weird. Ugly fruit. Wait. Oh, we were supposed to do kiwi fruit backwards. Did I miss that? Where did kiwi juices 5? Oh, right here, print reverse. I did kiwi fruit, but I didn't reverse it. So this was actually supposed to be, yeah, the reverse of that. Other than that, we got it. So, all right, we finished another chapter, and I'm going to stop right here because I think it's going pretty long. Okay, so yeah, we're making good progress. We're starting to fly now. So talk to you all next time. Thank you. Bye.